Okay, so this is the second half of the Algebra 2 final review for semester 1. We're going to be picking up on question number 14 and 15, where we're going to be asked to do some graphing. 16 and 17 as well. So the next few problems are all based on graphs, which we can use our graphing calculator to help with. But number 14 is y equals negative 2x plus 3 squared plus 9. This is a parabola, and you're asked to also state the vertex. If you've been doing the worksheet, the homework, or the test review along with me, you should be able to find, if you've been doing the test review with us, you know that the opposite of what's with x, since this says x plus 3, it'll be negative 3, and since this says plus 9 at the end, it'll be a positive 9 for my vertex. You can also find that in the graphing calculator as we go to produce the graph. But this tells me I can come over here to negative 3 and up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 3, 9 will be right there. Give or take. I'm going to use my calculator to help with this process anyway, so let's go in and do negative 2 parentheses x plus 3 close parentheses squared plus 9. If I graph it, sure enough, that's where the vertex is, over here at negative 3, 9. In the table, I want to put negative 3, 9 kind of in the middle of the screen. And you can see the symmetry of the 7s and the 1s. So I'm going to go ahead and plot negative 5, 1 and negative 4, 7. Negative 5, 1 would be right there. Negative 4, 7 would be right around there. And there's coincidentally other points like negative 2, 7 and negative 1, 1. And that should be enough for me to create a really bad parabola. Did a really bad job on that left side. Try to give me a little bit of credit. But anyway, that's what your parabola should look like with the vertex stated. The next question, number 15, is a polynomial, which will have several bumps along the way. It says y equals negative x, parentheses x minus 4, x plus 2, x plus 6 squared, and x plus 8. If I go, listen, on the test review and on the test, it'll say things like LCD, EB, zeros, mult, and TP. This is just a way to gather your thoughts. You do not have to fill it out. But for instance, the leading coefficient in this problem would be the negative sign. So it tells me that the leading coefficient is negative. If it's not negative, it's positive. So it's a pretty simple deal. Next thing we look for is the degree, which is the number of x's in the problem, or if we FOILed it out, the biggest exponent. So x times x would make x squared, times another x would be x cubed, another x would be x4, but it's squared here, so it's x5, and then one more would be x6. If you count your x's, there are 6 of them, if you remember to double count the squared value. That's an even number. That allows me to find the end behavior, or the EB, the two arrows. When the leading coefficient is negative, the right arrow will go down. If it was positive, the right arrow would go up. Even means that the two arrows will match because there's an even number of socks in your laundry. So this arrow would also be down. The next thing is the zeros. The zeros are whatever make each of these x values. If I plug in a number for each of these, I'd want each value to become 0. So for instance, x plus 8 would be 0 if x was negative 8. X plus 6 would be negative 6. X plus 2 would be negative 2. X minus 4 would be positive 4. And the one that everybody always seems to forget, when there's an x without a plus or minus, it's not added or subtracted with anything, that means it's 0. So 0 would be a 0. Multiplicities occur when a 0 is repeated. Because of the x plus 6 being squared, the value at negative 6 will have a multiplicity, and then the number of turns or turning points for TP, and the number of turns is 1 less than the degree. Since the degree was 6, we will have 5 turns. Okay, so I'm going to go ahead and produce the graph, which I could do without listing all that side information, but just trying to be transparent about everything. I should have a 0 over here at 2, 3, 4, 5, 6, 7, 8, negative 8, negative 6, negative 2, 0, and 1, 2, 3, positive 4. My arrow on the left should be down. My arrow on the right should be down. And then the last thing to think about, those zeros that are multiplicities, the multiple zeros, that value has what's called a Welch indicator. You don't have to draw that dotted circle, but I draw it to remind myself that when I hit that, I'm not going to pass through. So I'm going to come up from this first one, go through at -8, come down. I'm going to bounce at -6, go down through -2, up through 0, down through positive 4, and my arrows match what they're supposed to. I can tell there's 5 bumps along the way. This is the graph. All right, let's look at question 16 and 17, more graphs. But these are square root and cube root graphs from chapter 6. So number 16, we've got y equals square root of x minus 3 plus 4, and 17 has y equals the cube root of x plus 2 plus 3. And in both cases, we're asked to give the domain and the range as part of our graph. We'll come back to those in a minute. When I'm graphing this square root graph, we can go straight to the calculator. There is some information we're going to need, but it might help us, it might spark some ideas if we had the image in front of us. So square root of x minus 3, out of the square root we write the plus 4. So make sure you get out of the root. When I graph this, this is that graph that starts at a single point and drifts to the right. So I need to know where that point is that it starts at. It's easy to look at the equation and find it, but it's also easy to look and find the first non-error, which is 3, 4. So the point 3, 4 is going to be my first value of importance. 2, 3, 4, right there. You can also tell because it's the opposite of what's grouped with x and the number at the end. Just like finding the vertex of a parabola. That 3 and 4 are going to be important points when doing the domain and range. We'll come back to what to do in the middle of those here in a second. But x will be related to 3, y will be related to 4. I need some more points to plot. Let me get the right thing. Nope. Calculator. There we go. I could plot points like 4, 5, and 7, 6. So I'm going to go ahead and plot those. 4 should be at 5, and 5, so that's 5, 6, 7 should be up at 6, be right around there. And so that's enough to create this half parabola on its right, on its side, drifting to the right. Now you'll notice the direction that we're pointing is to the right. That is the direction of the arrow for the x. It is to the right or equal to 3. It can equal 3 because there is a point at 3. The y is trending upward. If we look at these y values, they are getting bigger, right? They're going up the scale, which means we would also have a greater than equal to for our y. If it was dropping and going down, the y value would be less than equal to. But the x is always greater than equal to. That's not going to change. Over here, when we do our cube root graph, same thing. I'm going to go to my calculator. For a cube root, that function exists in the math key. Option number 4 should look like that. Cube root of x plus 2. Get out of the cube root, plus 3. And if I graph it, this is that S-shape curve, the double bend in the middle there. You may or may not remember, but there are no restrictions to the domain and range. So we can use the fancy R to mean all real numbers. But I need to know where this graph is centered in that double bend. And it's going to be over here somewhere. Sure enough, if I look at the equation, it's the opposite of what's with x, which would be -2 and whatever is added at the end. So -2, 3 is the center of my graph, if you will. And when I look at the table, if I put -2, 3 in the middle, I can get points around those values. So, for instance, -3, 2, be right about there. 1, 4, be about there. But those are all in a straight line. You need at least one more point on each side. So if I go out here to -10, I'm at 1. So So that's 3, 4, 5, 6, 7, 8, 9, 10. I'd be at 1, which is around there. So you can kind of see this side of the tail going that way. I know this side's going to come up and go this way, but I need more data. If we go out to, I believe it's 4 or 5, probably 5. Oops. Let's go down here. 6 is at 5. So 4, 5, 6. I'd be up one more point up here. And so you can kind of see this drifting off to the right here. There's our graph. Again, 5 points on that one. Domain and range is all real numbers. Okay, we get to take a break from graphing and start doing some more just algebraic things. Number 18 asks us to find an inverse of y equals 5x cubed minus 13. To find the inverse, we're going to trade x and y places. So it becomes x equals 5y cubed minus 13. Now we're going to peel the layers. We peel these layers according to SADMEP. We do addition, subtraction, multiply, divide, then exponents and parentheses. So the first thing I can do to make my life easier is to just add the 13 over. This becomes x plus 13 equals 5y cubed. I want to get rid of this y cubed, but I also have to get rid of the 5. According to SADMEP, we did addition, subtraction. The next thing would be multiply or divide. So we're going to divide everybody by 5. Produces x plus 13 all over 5 equals y cubed. And to get rid of a cube, I'm going to cube root. And when I cube root, I want to make sure I cube root the entire thing. So my final answer would be y inverse, which would be y to the negative 1. Sometimes you'll see it g to the negative 1. It depends on what the equation was named. This was named y to begin with. So we'll say y inverse is the cube root of x plus 13 all over 5. You can tell everything is in the root. I don't have anything sticking out. Okay. Number 19 is going to be about function notation. So we've got an f of x that's equal to 2x minus 8 and a g of x that's equal to x squared minus 9. And I'm asking you to find f of g of 3. The way this works, 3 is going to go into equation g. So I'm going to take this equation. I'm going to find g of 3 by plugging 3 in for the x value. So this becomes 3 squared minus 9. Well, 3 squared is 9 minus 9 is 0. So 3 went into g, and what comes out of g is now going to go into f. So I'll take f, but instead of putting in an x, I'm going to plug in 0. The answer from the g equation becomes the input for the x equation. 2 times, instead of x, I'll put 0 minus 8. 2 times 0 is 0, minus 8 is negative 8, and there's my final answer. So that notation, f of g of 3, is a double substitution. All right, we're getting close, guys. This one is not going to take us as long. Number 20, we're supposed to solve for x. It starts with 3x plus 6 raised to the 2/3 plus 4 equals 13. And our job is to solve for x by peeling the layers off. If we think about this 3x plus 6 to the 2/3 as a chunk of information, I'm going to have to get into that, but I can't get into it if there's anything outside of it. There's the 2/3. That's part of that parentheses, but this 4 is not. So I'm going to remove the 4 before I try to do anything else. That is going to make my life easier because I'm only going to have one number outside of the parentheses. And 13 minus 4 is 9. Now I need to remove the exponent so that I can get into the parentheses. The way we remove it is by raising it to its reciprocal. The reciprocal of 2/3 is 3/2, so we're going to raise it to the 3/2. That'll leave me with 3x plus 6 equals whatever 9 to the 3/2 is. So 9 raised to the 3/2 is 27. I can now do basic algebra by minusing 6. 3x equals 21. Divide both sides by 3. And x x must equal 7. All right, last page, last little bit. 5 problems left. Here we go. This is where we get into chapter 7 and all of our logarithm and exponential problems. So on number 21, we've got y equals negative 2/3 e to the negative x plus 2. We want to graph this and give its domain and range. I'll use my calculator to help with the process. So, whoops. That was a little extra. It's okay. We'll go to our y equals, and we're going to do negative 2 divided by 3. E is the second function of ln, and I'll put a negative x here, and I'll get out of the exponent plus 2. If I produce that graph, it looks something like this. A nice decay graph as it comes up and flattens out. I need 2 points and the boundary line. If I look for the 2 points, there's lots of points. They're going to be decimals, but I'm going to go ahead and plot negative 2, negative 2.9. Negative 2, negative 2.9 would be right around there. And then I think there was another point at negative 1.18. So that would be just barely above the x-axis. So I got those 2 points there. I also need to know where the boundary line is. Well, the boundary line is whatever is added or subtracted at the end. This says plus 2, so at positive 2, I can come in and draw my boundary line. Okay, that's going to have something to do with my domain and range here in a minute. But I look back at that image, and I know it was flat here on the right and curved down. So I'm going to follow the curve, follow the flat line. Whoops, excuse me, I'm getting a little drifty. It's hard sometimes to draw this with a mouse. All right, so there's our graph to give our domain. There are no restrictions on the domain of an exponential graph. However, the range is restricted. This graph is always below, or less than, our boundary line at positive 2. Never equal to, because we don't touch the dotted line. We just approach it from below. Okay, we're done graphing. These last few problems are all about logarithms and exponentials. What is that? That's weird. Okay, let's grab 22, which says we want to write 3 equals 4 to the x as a logarithm. So it's log, parentheses, equals. All right, if you remember, b to the x equals y is interchangeable with log base b of y equals x. I want to write this log form, but I need to know what my base, my y, and my x are. So everybody has a position, so you can kind of say, okay, who's the base in this problem? Well, the base is the thing that holds the exponent up. In this problem, the thing that holds the exponent up is 4. So 4 would be my base. And then the y is what ends up in the parentheses, and y is what the exponential is equal to. Well, my exponential 4 to the x is equal to 3, so 3 is going to go in the parentheses, and that will equal the exponent x. You could evaluate this, but I'm not asking you to. I'm just asking you to write it as a logarithm. This little line is not going to go away, but that's okay. We can work around it. If we were to look at question number 23, we're supposed to expand a logarithm that has several pieces inside of it. It's a log base 3 of 4x to the 4th over 3z squared. One of the suggestions I had when we talked about this earlier was that you put a multiplication sign anywhere that it's implied. This is like 4 times x to the 4th. This is 3 times z squared. That tells me that there are 4 unique pieces inside of this logarithm. So I'm going to separate it as a log base 3 4 times. Once for the 4, once for the x to the 4th, once for the 3, and once for the z squared. I now need to determine whether these are pluses or minuses. Everything that comes from the numerator is plus. So the log base 3 of 4 was on the top, so it's positive. And the log base 3 of x to the 4th must be positive. But the 3 and the z squared, they came from the bottom, so I will minus both of those. The one last thing we haven't done on this problem is look for exponents. Exponents always get dumped in front of the logarithm that they're part of. So these exponents would go in front. My final answer would be log base 3 of 4 plus 4 log base 3 of x minus log base 3 of 3 minus 2 log base 3 of z. All right, so that's the fully expanded logarithm as we go. Last two, just solving a logarithm and an exponential. Okay. If we look at number 24, we got 4 to the 3x plus 5 equals 256. What we need to know is our exponential alone. The exponential should have the exponent and its base. But there's nothing else on this side of the equal sign, so I'm ready to start transitioning this into a logarithm. If I write this as a log, the base of my log will be 4. The thing that goes into the parentheses is what it's equal to, which is 256. And it's equal to 3x plus 5. The log base 4 of 256 can be put into the calculator. Grab my calculator. And the fancy way to do it is to push the math button, go up to where it says log base. Oh, got to get out of there, sorry. Math, go up to log base. We can do a base 4 of 256, and that gives me 4. So my equation is now 4 equals 3x plus 5. So I'll minus 5 from both sides. Negative 1 equals 3x. And I divide by 3 to get x equals negative 1/3. You could write that as a decimal, 0.3 repeating, or you could just write it as negative 1/3. 25 is the same thing, but in reverse. Here we have a log base 6 of x minus 3 equals 3.6. Is the logarithm alone? The log should have a base and a parentheses. Nothing else is allowed over here on this side of the equal sign. It is alone, so I'm ready to write this as a b to the x equals y. Remember that when we're building logarithms, b is the base, y is in the parentheses, and x is what it equals. So if I'm trying to build this pattern over here, it would be 6 to the 3.6 equals x minus 3. Well, 6 to the 3.6 is a calculator problem. So 6 raised to the 3.6 is 632.9137. 632.9137. Did I do that right? Yep. That equals x minus 3. To finish, I'm going to add 3. So x would equal 635.9137. Typically, we like to have 4 decimal places in our logarithmic answers. Okay, good luck, guys. We'll see you in class.